squared. I did 2 times pi divided by 5.
2 times pi divided by 5. So if you're doing 2 pi divided by 5, it sounds like you're using, it takes 5 seconds to go all the way around?
Yeah.
Yeah, well, it's not gonna take 5 seconds to go all the way around. I think that's where part of it falls apart. But you also, it sounded like you were finding the speed, angular speed, instead of kinetic energy. I think you were finding something else.
Okay. All right. That's right.
Okay. Well, we try to connect the potentially disparate topics at the moment.
Okay.
If I have an object, let's go back, since a 5 kilogram mass going at 4 meters per second, and I have another mass right here going at 2 meters per second, let's make that also 5 kilograms. What is the total kinetic energy? That one would be 40. I think those are the same numbers we used before, isn't it?
Yep.
Yeah, but the total. Sorry?
50.
So this has kinetic energy is 40 joules. Kinetic energy of this was 10 joules. So the total 50 joules. The biggest mistake I see students make when they're plugging into 1/2 mv squared is they'll do 1/2 times the mass times the speed, and then they square it, squaring everything. Only the speed gets squared. All right, so if I ask for what is the total kinetic energy, if I can break it nicely into 2 parts like that, it's, it's extra work on the calculator, but it's not mentally strenuous in the fact that if you can do one, you can do the other one. Borrowing Carol Sayers. So that in essence is an approach here so if I have this object here that's falling, if I can just break it up into smaller parts, I can get a much better approximation. So if I break it up into 2 parts, and so let's say that this is going 10 meters per second. That means it's going 5 meters per second here. It's going 7.5 meters per second here. It's going 2.5 meters per second here. That's a quarter of the way, half the way, 3/4 of the way, all the way. Then I can get somewhat of an approximation here by just doing, well, the bottom half, let me just use 2.5 meters per second. The top half, let me use 7.5 meters per second. And so let's give it the whole thing a mass of some number nicely divisible. So let's make it 12 kilograms. So this piece right here is 6 kilograms. So the kinetic energy of this piece, we're going to estimate it as 1/2 times 6 kilograms times 7.5 meters per second squared. And down here, this piece, that kinetic energy, we're going to approximate it as 1/2 times 6 kilograms times 2.5 meters per second squared. And we will get closer than if we just did 12 kilograms times, or 1/2 times 12 kilograms times 5 squared. And what is this? Say it again.
187.5.
Okay. If we had done this same technique with the whole thing, just so that we have another number here. So if we just did a crude estimate of, let's just take the middle point, we would have had 1/2 times 12, because we're looking at the whole thing, times 5 meters per second squared. So that's 25. 150. Now, obviously, this was a gross estimate because we just looked at the whole thing, picked the middle point. This should be a slightly better estimate because we're breaking it up into parts. How can we make an even better estimate?
Putting the 4 parts?
Why stop there? So what the math people figured out was that they are going to break it up into as many parts as possible. Now recognize each part, the more parts they break it up into, the less the mass of each part. We get more accuracy for how fast that piece is going, but the mass gets smaller and smaller. And so this is what it looks like. They're going to take this and they're going to break it up into an infinite number of pieces.
I got a different number than
Okay.
187.
What'd you get?
168.75.
You add them together.
Oh, and the bottom one too.
Yeah.
Oh,
So
okay.
that's just the top one?
Oh, yeah. Okay.
And I assume the difference is the bottom one.
Okay.
So we're going to take this stick and imagine it's broken up into an infinite number of pieces. However you want to do the hash marks. I have my rotation point right here, and so the kinetic energy, we're just going to add them all up. We got some spot down here, which I'm going to call spot number 1, then we'll have another one, I'm calling 2, and so on. So it's going to be 1/2 times the mass of whatever piece 1 is, times the speed of piece 1 squared, plus 1/2 times the mass of piece 2, times the speed of 2 squared, plus however many I break it up into, 1/2 of, what the heck, we'll break it up into an infinite number of pieces. Obviously, if we wanted to do this on a calculator, that would take the rest of your life. So we are heading towards a shortcut.
Do we always have to do it like that?
Do it like this?
Yeah.
No, I'm heading towards a shortcut.
Oh,
I just want to sort of explain where the shortcut comes from. Although it's not going to seem like a shortcut till the very last moment. Now there is one thing that all these pieces have in common on this stick that's falling over is the fact that the angular speed is the same. If it's, again, assuming a rigid body, and if that thing rotates, they're all going to be rotating together. We're not dealing with water where if you swirl it, the water doesn't always swirl together. Or if this were made of rubber, a piece of rubber doesn't always move together. So my speed is, my linear speed is different, but my angular speed is the same. So all these V's here, what I'm going to do is I'm going to put in omega r. That's what we talked about a little bit earlier. The fact that the linear speed is equal to omega times how far it is away from the center. And so this becomes 1/2 times mass 1 omega r1 squared plus 1/2 mass 2 times omega r2 squared plus now obviously that's a lot of writing to do. There's got to be a simpler way of writing it just so I don't have to keep writing this over and over again. And there is. If I'm adding up some pattern like that, this is what the math and physics people, well, the math people, the physics follows. They will use this symbol to mean I'm going to add a bunch of stuff up. And what I'm adding up is 1/2 mass, I'm going to put a little subscript there, I, omega r sub I equals 1 to whatever the top is. This is just the shorthand notation for actually writing this entire sequence out. 1/2 m and omega and r are common to every single term. The Greek letter right there is a capital sigma.
All right. Question?
So, when you have the, multiple numbers that you're adding together, how does that translate from just the WR squared, or the WR,
Oh,
subscript?
how does it go from here to here?
Yeah,
All right, so the first term I have ones there, the second term I have twos, next term would have threes, and so on. The I is just a placeholder,
okay.
and this tells me I start with I is equal to 1, plug a 1 in, plus, then I go to a
So
2,
you
plug a
would
2 in.
add on to that
Yeah.
as well, okay.
Yeah, this is the summation symbol, and it's just a shorthand that I'm gonna add this for that value all the way up to that value.
Okay. I didn't see the infinity up there.
It's sort of hidden there, different sheet somehow.
What's the big size? Is that a that's part of that?
That's an infinity sign. I'm breaking up into a bunch of pieces. And if you find infinity uncomfortable, make it a million. Make it just some huge number. We're taking this and breaking up into tiny little bits. So because we can find the speed of a tiny bit much more easily than this linear speed of an entire thing. Was that question answered?
Yes.
Other questions?
Can you explain that definition again?
The V equals omega R?
Yeah, that's.
So this is linear speed. This is angular speed. And this is, in essence, a radius. This is the distance to the pivot point, or axis of rotation. So if I were closing the door here, this would be the pivot point, and R would just be the distance. So if I wanted to find the linear speed of that screw right there, R would be that distance from the pivot point to where the screw is. Omega would be a measure of how quickly that thing's opening. And then I can find the speed of that screw, the linear speed.
I have a question.
Yeah, kind of.
So radius is typically defined as like halfway, like from the pivot point, so it's not always halfway, it's gonna be whatever you're looking for?
Yes.
Okay.
Yeah. It's the radius of the circle created by that particular spot. Other questions? All right, gonna do another trip down memory lane in math. Yeah. Makes life worth living. I think those were self-absorbed.
If I have 2x plus 2y, if I have something common to both terms, again, terms are things that are added together, factors are things that are multiplied together. So these are terms. What's common to both terms? If I have something common to both terms, I can factor it out. So this is the same thing as 2 times x plus y. If you want to go in the other direction, it's called distribution. 2 times x plus 2 times y. So this is called factoring. What we're going to do over here is, again, I got this infinite number of terms, and I have 2 things that are common to every single thing on there. All of them have a half, and all of them have this omega squared. I will stick in one intermediate step, and then I will factor out. So this is the sum, 1/2, make some I, omega squared, r sub I squared. Just squaring both things in the middle. The 1/2 and the omega are constant. They are the same for every single item of this thing that's folded over. I can factor it out. So I'm just going to pull it out front. and I get 1/2 omega squared times, what we're left with is m sub I r sub I squared. And that is the journey we were going on. Isn't this so much simpler than what we were doing before? I'm gonna go grab my textbook, and then I will talk about why that's simpler than what we were just doing.
What page you on? Oh, let's see.
It's gonna be page 138. All right, so why is it simple? Physicists can't let something go by without assigning a different letter. So this bit right here has a special name. First off, the letter that they use for it is a capital I. Obviously. This stands for, it has two names actually, moment of inertia, which is what I tend to call it, or rotational inertia. I'm seeing rotational inertia pop up more in textbooks within the past 10 years, but I tend to call it moment of inertia. I think your textbook calls it rotational inertia. And so what we have is the kinetic energy for something that is rotating can be summed up in the nice little formula of, a little r down there, 1/2 I times the omega squared. Now, so if I have a stick that's falling over, all we need to do is figure it out I. In other words, we break it up into an infinite number of pieces and think of what the mass is of each of those tiny pieces and the distance squared and add it to this infinite sum, and we're done. Or, you turn to page 138 in the textbook, and it's already been done for common shapes. So if I had a stick swinging about its end, there's the formula right there. Stick about end. I is equal to 1/3 ml squared. So we can find the kinetic energy. Let's say that is swinging about its end at 5 radians per second. So omega, like 5 radians per second. I, based on the formula in the book, is 1/3 ml squared. So 1/3 times the mass of the meter stick, which is roughly 100 grams based upon what you've seen in the lab, or in kilograms, 0.1 kilograms. The length of the meter stick, 1 meter. So therefore, what is the moment of inertia of the meter stick? Swinging about its end point.
I think 0.03 and all that stuff.
0.033 repeating.
Yeah.
Units. What are the units of this? Not KR. Not at least not accepted by the international community.
Is it radians per second?
It is not. Think about what we multiplied in order to get the 0.03 repeating.
Kilogram meters.
Yes, we have a kilogram here, we have a meters there, and the meter is squared. It is a kilogram meter squared. There's no nice one-word unit for it. So the kinetic energy 1/2 times 0.03 repeating kilogram meters squared times omega, which is, I said 5 radians per second squared. That will tell us the kinetic energy.
What, we wasn't done?
No, there's always more.
Okay.
Much to most people's rejoicing. With,
5 great rats.
I just,
Okay.
that should be radians per second, sorry,
Okay.
lost the slash. I just said, let's pretend that's what it is.
Okay, sorry.
Would it be 0.75?
0.75?
It's,
Anyone else get the same thing?
I got a different number.
What'd you get?
0.375.
So that's half that, did you multiply by the half? Anyone else get either of these?
Four, 16625.
416625?
Yeah.
Is there a decimal in there?
Point.
Wait, okay,
I don't get a feeling.
375
so we got 2 for that?
Yeah, I got 0.375, sorry.
Okay,
I didn't square the 5.
you got what? Wow. Oh, did you use 0.03 or 0.03 repeating?
0.03 repeating.
And to get this, did you use 0.03 or 0.03 repeating?
0.03.
0.03.
I think that's the difference between those
Oh,
two.
okay. We all got it right
Well,
though.
eventually. Units? What are the units?
Okay.
Would it be rads per second?
No.
No, okay.
Kilograms times meters squared times rats per second squared.
Okay, so let's put that down. Kilograms times meters squared, radians squared per second squared. There is a one-word unit for it.
Oh,
Is it I?
What did we just find?
Rotational inertia.